We shall look into one type of networks that's called precedence network. And why we call it precedence network? Because it is a network that contains all other types of dependencies between activities. And just put them back for you so that you remember the type of dependencies we have. We have always used two activities, two web packages, A, let's say A and B. One most common is this one, finish to start, with a lag or a delay, depending on the project. And then you have the second one, which we call the start-to-start relationship. And look how I draw the arrows. I start from here, and the arrows end up at the start point. It's always good if you draw it as the relationship says. You will be able to see what really happened with the activity. A and B, and again we call it SS with a lag or without a lag. And then we have the third one, which we call it finish to finish, when we have to finish two activities at the same time. Finish to finish with lag or without lag. And then we have the last one, which is known as start to finish. When we start something, we finish the other one. Start to finish. With lag or without. Now, in precedence networks, when you have these types of dependencies, then we call it a precedence network. So a precedence network is a special case of activity on node type of networks. And by the way, activity on arc, the A or A cannot handle this type of dependencies. The A only handles this, only. It's only the AON that can handle all the other activities. That's why this is the one we prefer always. It's easy, it can handle several types of activities. So, let's start with an example to show you how can we conduct the critical path. How can we use the critical path method when we have these types of activities? I have with me an example, and I am hoping that you can help me with that. So, we start with A, has a duration of 2, and then another one here is B, has a duration of 3, and we have another activity C, duration of 2, and we have a D, and it has a duration of 5. And then we have a E, duration of 4, and then you have an F, duration of 2, and then you have a G, duration of 5. That's a typical activity on node. And then let's put the relationships. From A to B, we have just finish to start. Nothing else. From B to C, we have start to start. And let's say this time we shall not put any lag or delay. And from C to D, we have start to start. Again. And then from B to E, we have finish to start. And from C to E, we have finish to start. And from D to C, we have finish to finish. And from D to F, we have finish to start. and this one has finish to start, and between these two we have finish to start. This is the network logic, right? So, how long this project will take if we want to adhere to all of these constants? Where we always begin, here, and we put, unless otherwise is mentioned or otherwise is given, we start with the 0. And again, to remind you, 0 here, there is no day, it's called day 0. But 0, we put it to refer to the beginning of day 1, the beginning of week 1, the beginning of month 1, and so on. So 0. Now, again, this advanced mathematics, the critical path, 0 plus 2 is 2. So, and what, just to, again, try to bring this into your heads. Early finish, early start, early finish, late finish, or late start. So what will be the early start of B? It is 2 plus 0, because nothing is delayed, then it's 2. And then we say 2 plus 3 is 5. And then you have start to start, 2. Then the start time for C is also 2. And then we have start to start. Then the start time for D is also 2. Now, we go forward. 2 plus 2 is 4. And we make a circle. Why I put a circle here, do you think? Because of this one. There is a finish to finish. So circle means it's temporary. We will see. And then 2 plus 5 is 7. And you have this finish to finish relationship. You have 7 plus 0 is 7. So you have two alternatives. It is 7 or 4. What we select always?
Longer.
7. The math. 7. So this means that actually this one is very dominant. It is this connection that determines the finish date for C, and not the duration of C. We can use this kind of information later when we are going to move resources from one activity to another activity in order to optimize our resources. Now, very good. Now, what will be the early start of F? It is, you have a simple finish to start relationship. It means 7. 7 plus 2 is 9, right? And we can stop a little bit here. What about here? What will be the early start of E? You have 5 plus 0 is 5, but you have 7 plus 0 is 7. We always take that max. 7 plus 4 is 11. And here we have 11 plus 0 is 11. But we have this connection here. So we have to first 9 plus 0 is 9. 9 minus 5 is 4. What we should take is 11. 11. 11 plus 5 is 6. 16. 16, and then, which means that now we know that our duration is 16. Now let's go back. Why we go back now? What is the purpose of going back? The purpose of going back is to identify the flows for each wait package. How much time we have available when we can move activity forward and backwards without influencing the total project duration. So we go back. And we start with 16 unless otherwise is given. So we say 16 here, 16 minus 5 is 11. So immediately you can see here that the early start of G is 11 and the late start is 11. And the late finish is 16 and the early finish is 16. Then this activity has 0 flow. Any change to the duration will make your project longer. This is what it says. And then let's go back. We just follow the arrows back. I start from 16. So the late finish here is 16. I go back. Nothing else. There is other connection. Then the late finish for F should be 60. And 16 minus 2 is 40. And we can stop a little bit because you see here you have two connections. We have to examine them. And then we look here. 11. Follow the arrow. It's 11. 11 minus 4 is 7. And now, follow the arrow. 7 minus 0 is 7. Is the other arrows? No. This one goes back from. So we have here, it is 7 or 14. From this connection we get a 7. From this connection we get a 14. Which one we should select? The smallest one, which is 7. 7 minus 5 is 2. Very nice. So let's continue. What about this and this? 7 minus 2 is 5, right? But you have something is coming from this one. 2 minus 0 is 2. Which one we select? 2. This is interesting. And what else? 7, we go back with this. It becomes 7, right? There's no other connection. And 7 minus 3 is 4, but 2 minus 2 is 2. And here you see, here you are locked. And here you are free. And then which one we choose? Of course, 2 and 3. So what is the critical path now? What is your critical path? Critical path is the path with the least flow. This one is critical. Obviously, it's critical. What about this one? No, this one is not critical. What about this one? It is critical. What about this one? Is it critical? Yes, it is critical because the end date is locked at 7. And the start date is locked at 2. Although, you see, your only duration is 2. So actually, it means here this activity, because it is locked, you have to early finish is early start is 2, and the early finish is 7, and the late start is 2, and the late finish is 7, but your duration is only 2, which means that here this could be corrected. It can be. This network logic is not supported in this case. So this one should be adjusted to match the network logic. Otherwise, something will go wrong. And then what about this? This one is have a float of 2. And this one have a float of 0. So your critical path actually, based on that, should be A, right? C, E, and G, or A, D. Actually, I can put them together since this line here. A, C, D. Which path I should use now? A, C, E, G, A, C, G, or A, D, E, G. These are your critical paths in your. Let's look at, I want to show you something that it might help us to understand what is the meaning of these numbers, so that you just grasp the idea, because next lecture we will look into, yeah.
You don't have B on the path.
No, B is not there. B is not critical.
Yeah, but it's on the paths of activities that need to be carried out.
What do you mean path?
I mean, the sequence
how
of
you go
activities.
from A to B?
How do you get from A to B?
right?
No, it's not that way of thinking. It's not this way of thinking that there is this connection. But they are activities, right, in the networks. You don't have to go from A to C through B. You know, when we say a path, it's not necessarily they are physically connected. But you see, A and C, they are physically connected through B. But B is not on the critical path. It has possibility to extend the duration of B. But you can do that for C. Actually, C, this 2 is wrong. This should have been 5 in order to match the network logic. So it shouldn't be physically connected. What do you mean? There are a series of activities. If we start A, then our possible way is through this SS, and then end up here. Then C, and then I go to E, and then I go to G. Or the other one, I go from A, and I jump these lines, and then I go to D, and then I go to E. That's how the concept of a critical path. Actually, you should think of critical activities would be more correct to say. Critical activities rather than critical path. But what I wanted to show you here in this example, actually, what these numbers mean. What actually the significance of these numbers. It says here that B. Now, you have like a bar. Do you like fishing? Yeah? You have boats, right? When you go fishing, you sit in a boat, and then when you finish fishing, you go to the place where you park your boat. What's that called? The wharf. This is the wharf, actually. Think about it like this. This is the available place for you at the harbor, where you can go and put your boat. In this case, if you look at B, it says your wharf, the place where you can park your boat, has a total length of start, for instance, from point 2, and it extends to point 7. So the total, how can you see? The total amount of space available for you to park your boat is 5 meters, okay? But you have a small, tiny little boat, and it's only 3 meters. Which means that in this case, you can actually have your 3 meters like this. right? And you can put it anywhere between these 3 meters. You can start here, you can put your boat here, and if you put your boat here, then the total place you need, it will be only 2 plus 3, which is 5. Then you will have additional 2 meters. If you want to move your boat, you can move your boat. But that's one way to think about it. Another way to think about it, you can tell yourself, since I have all this space, why I can't go and get myself a bigger boat? And this way of thinking, when you say, why I can't go and get myself a bigger boat, in project management, it is the same as saying, let us extend the duration of this activity. Why do we have to press all our work so that it can be completed in 3 weeks when we actually have the ability to complete it in 5 weeks? And this idea is what we actually utilize when we are performing resource planning. So when we are performing resource planning, we go and look into our network, how our resources are being used. And then maybe we discover at some certain points in time we don't have enough resources to cover all our activities. Then we think, aha, we can take advantage of this flow. Let us extend project duration, reduce the resource needs within this period of time so that we can compensate for lack of resources. This is why we need actually to determine the float for each activity, to take advantage of that when we produce or when we work on resource planning, which we will see a little bit today. Let's take another example, okay, before the break, to maybe understand it a little bit, to get the graph of it. Now I will make it not too big this time. Just I want to illustrate one point for you I made earlier today in the Kahoot. And this is finished to start. And let's say this is finished to start. And this is finished to start. But this is one is finished to finish. And this one finished to finish. Correct? That's our network. And we say that this is our A, it's 5, B is 5, C is 5, and D is 5. And let's put the data here. 0, 5, 5, it's ordinary relations here, 5, 5 plus 5 is 10, 5 plus 5 is 10, right? And then you have finish to finish is 10, and so it is the same thing, nothing happened, correct? And here, what should be the early start for D? You have 10, or you have 10 minus 5 is 5, then we should take the 10. 10 plus 5 is 15. So the total project duration is 15. What if I tell you now that your clients told you that, okay, you have 20 weeks to complete your project. That's the available time for our project. And what should we put here? 15 or 20? It's 20. That's the rule. Here you put your maximum late finish. That's what is available for me to finish is 20. And then we go back and see what happens. 20 minus 5 is how much? 15? Correct? And then we go back with this, 15. And then it becomes how much here? It should be 15. Correct? But then what we go from here? We have this one. We have 20. Then here should be 20. Correct? And then we go back. 20 or 15? 15. Then this is this is the dominant. And then 15 minus 5 is 5. And obviously 15 here. Huh? Yes. And then we go back and with what it will be 10 or 15 is 10. So let's look at the float here. Here you have a float of 5. Here you have a float of 5. Here you have a float of 5. And here you have a float of 10. What is the critical path? This is the critical path. Although it is not 0. Although it is not 0. Because it can be at any time critical. If I tell you, well, they changed their mind. They want it in 15 days. Then it quickly become a critical path. The first thing that is affected.
Delayed start from 8 to 5?
Yeah, it's 5. So. And you know what we call this? Is we call it the subcritical. It's not critical, but this is the one which is, if anything happens, it can become critical. If, for instance, we increase the duration of B. So the things that is about to be critical, we call them subcritical, and all the others, the one with the least float, is what we refer to them as the critical activities, or the critical path. Now, in the next lecture, what we will look at is the crashing. How can we expedite? Now, as you can see, I have a project duration here with some float, right? And maybe we would like to speed up this particular project. How can we do this speeding up? How can we optimize time and costs? Let's take a 10 minutes break and then come back. So when we have this, all these types, or some of them at least, in one network, we call this network a precedence network. It is a special case of activity on node networks. Here, it is the way we go forward or backward is the same. You just have to be a little bit more careful when you do the calculation. And by the way, this is important for the exam. So you should learn this way. Okay? Just to say that, I have to say it. So it's not a trivial assignment. And then there is another tool we use in order to show time relations in a network or in a project, and it's called Gantt chart. Actually, this is a very, very old method. It was developed, I think, in 1899 or something like that. It's like 100 and a lot years old. And it's still useful. And it's useful because it's a good tool to communicate the project. Here As you can see, the bars, the horizontal bars, they represent activities, and the length of these bars represent the duration of each activity. And as you can see, we can put some arrows to indicate the relationship, the finish to start relationships. This kind of diagrams are very good, very effective communication tools. It shows us the entire project actually in just one page. But the disadvantage with this Gantt chart, it fails to represent, it fails. We will not be able to see or to identify the critical path if we have other type of relationships other than finish to start. As long as you have finish to start relationships, you will be able almost to see the critical path. Because you just look for these ones with the longest duration. But when they overlap, as you saw from the previous examples, then the longest duration might not become very visible. But it's good to communicate your project if your project is not that complex. And then comes this crashing. Crashing is simply, in many situations, when you define your total project duration and you identify your critical path, and let's say your critical path is 60 weeks. And then somebody tells you, no, you cannot complete your project in 60 weeks, you have to complete it, let's say, in 50 weeks. Then you must speed up. You must hurry up. Some activities must be run or produced in a faster time. And then, of course, in order to do that, what we always need? We need additional resources. Over time, right? Maybe we need to change the way we work. Maybe we need to hire some consultants, some people who can help us to produce the work faster. So all that costs money. That's for one point. The second point, which is important to remember, when you crash, you can't really crash until the duration becomes zero. No, there are limitations on how many days or how many weeks you can crash an activity. So we can't crash it like 100%, otherwise it means eliminating the entire activity. And number two, crashing costs money. Then what we want to do actually is we try to balance how much money are we going to put in order to accelerate this project. You have a project that should be completed in 60 days and you say I want to complete it in 50 days. But completing it in 60 days costs you 100,000 and completing it in 50 days costs you 200,000. Are you willing to pay that difference? And what is the optimum cost that you are willing to pay? This is the idea of crashing. How do we crash? The crashing itself is just an optimization problem. In order to crash, you have to find out the total costs, the variable cost, the fixed cost, all the other costs, and then the fully crashed activity is the one which is fully expedited. And then you do optimizations between trade-offs. Let us illustrate this problem with crashing with an example. Now you have a network here, and usually when we do crashing, we have to identify, as you can see from this diagram, you have to identify the normal cost, normal duration, and the crashed cost and the crashed duration. What this diagram says to us. Say, look at A, for instance. A, this is money, and this is time. It says the normal duration of A is 5. So let's count. 1, 2, 3, 4, 5. That's the normal duration. And then it costs you 1,000. So this is 1,000, and this is 2,000, and this is 3,000. So this here is your normal situation. Here is A is located. And then it says, if you crash, you can crash only 2 days. Of course, we cannot crash alone. In this case, 2 days. So your option is to go from 5 to 3. But if you want to do that, your total cost will become 1,500. So here is your crashed A. Here is your normal. This line here, we call it the crash gradients. The crash gradients actually tells us how much money we need to crash one day. That's what the idea of this crash gradient. So this gradient is equal to crash cost minus normal cost divided by normal duration minus crashed duration, which is in this case 200. So for A, your cost loss gradient is 250. You need 250 kroner or dollar in order to crash it one day. Now this example is in front of you, and it says here the total cost, the normal cost when you crash without crashing is $22,450, and when you crash all of them, you get 30,500. Now, which one of these should be crashed? Is it any game to crash them all? Or which one of these we really want to crash if we want to reduce the critical path to make it as short as possible? Which one of these should be reduced? Any idea? Yes.
B.
B, you want to reduce B. Why B?
Because it's least cost.
Least cost. The gentleman above there, he says, if you reduce B, you get, what will be the cost gradient for B? 300. And what's the cost gradient for A? It's 250. So actually it's cheaper to crash A rather than B. Look, always in order to distinguish between two activities, look at the crash cost. For B, the crash cost is 300 for 1 day. But for A, the crash cost is how much? 5 to 3, 500, 250. So no, it's not B. So which activities should we crash?
We should determine all the crash gradients for all the activities, and then we pick the lowest and the activity.
You are half right. First, you should define the crash gradient, yes, for all the activities, but before we crash, we have to find the critical path. We only crash the critical path. Why? Because it's the longest one. There is no any point in crashing B. It is not on the critical path. If you crash it, it is just more costs for you. So in order to understand the problem of crashing or to start crashing, the very first thing you should do is to draw your network. There you will be able to see your critical path. And then we will do exactly like Olmedo, right? Olmedo said, and he said that you select the ones with the smallest cost gradient. Exactly. That's what we do. Find your critical path, find the smallest cost gradient for each one of them, and then voila. The rest become too easy. So, this is our network. This is actually, I will have to draw your network before crashing, and I will draw your network after crashing. This is after crashing. Okay, let me draw your network. You have A, and this duration of 5, right? And then according to the diagram given in the textbook, B is 7, and C is 3, and D is 5, and E is 9, and F is 4. See, this is all normal durations I put here. And G is 6, and H is 8. And here you have your, it's all of them finished to start. That's easy to handle, right? And do like this, do like that, do like this, and then ta-da, ta-da, and ta-da. Okay, now you are the expert. What is the total duration of this project? Huh? Anyone has it in his mind? Super duper student. 19, 12, 16, 10, 16, 19, 27, go back, 27, 19, 19, 19, 10, 19, 15, 15, 15 minus 7 is 8, and then 19 minus 6 is 7, is it? How much 19 minus 6? 13. And then 13, it should be 10 here, it should be 5 here, it should be 10 here, it should be 5, nah. 7, and then this is 5, and this is 0. And as you can see, this is your critical path. This is the one that really matters if you crash. All the others, they don't matter too much. Unless you crash this too much. So your critical path is A, and D, and E, and H. So if you want to crash, you only crash this. But yes.
What if the critical path changes when you crash?
When you crash and you change your critical path, you have to go and look again what is the new critical path. It's usually like this. You get the assignment and says, crash this project with 20 days. When you crash the original critical path, let's say with 15 days, more than 15 days, another path takes over, correct? Then you will have to look at what other path that has taken over as critical path, and then you crash the new critical path. All the time, keep your eyes on what critical path you have into your network. Immediately, if the critical path changes, go to the new critical path and crash them. Following the same procedure. the cheapest one first. When I say cheapest, I mean the one with the least cost gradients. So what about here, guys? Now let's make a diagram or a table to define the cost gradient for your activities. We agree that we don't really need to crash all of that. We only need to crash A, D, E, and H. So let's say E, A, D, and E, and H. And this is our cost gradient. And here, as you can see, it is 1500 minus 1000 divided by 2. 5 minus 2, right? Which is how much? Bigger? Yes, like this. 250. And what about D? You can't crash it. It is 3 or 5 and it's locked. What about E? It is 9,000, right? Minus how much? Minus 3,750 divided by 9 minus 6, which is 3. How much is that? 1750. And then H is the expensive one, which is 15,000 minus 9,000 divided by 3, which gives you 2,000. So now here comes the trade-offs we have been talking about. The project total duration originally was how much? 27. Let's draw now everything to see what can we crash and what shouldn't we crash, and how this will impact our crash diagram. So let's draw. And here we say 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, right? More. 25, 26, 27, 28. This is our youth duration. And then from the numbers you can see it is 22,450 when we get this number. When we get it. When the duration is equal to, let's see, here is 10, here is 20, here is 30, here is 40, here is 50. Okay? So you get this 22,000 if your project duration is 27. So this is the least cost but with the longest duration. Now what happens if you crash A? What will be the impact if we want to draw this on this diagram? What if we crash A with 2 days? What will be the impact on cost? So we just crash it, we earn 2 days. Right? It becomes here. But how much cost we have to pay a little bit more? It's 500 more. So it is not very much. So this is our crash A. And then, if we crash E or A, what happens to us?
Just there, then the cost is per day. 250 is per day, not for the 2 days that you showed.
Yeah, and
Okay.
this is, if I may, 500, but you know, I put a scale which is huge here. So I'm not able to show it, but you are right. It's 500, it's 250
Per day.
Per 2 days become, I have actually I wrote it somewhere here. The exact number. Yeah. Then here, this is your 22,400, 450, and this becomes 22,950. Correct? And then you have to crash E. And how many days we gain if we crash E? 3. Very good. Then we go 25, 24, 23, and 22. But how much money we have to pay in order to do that? It is 1,750 per day multiplied by 3, and this gives you something like, I think I should have drawn it with a little bit more here, become here, which is the total cost become something like 27,750. This is crashing A and E. And then if you crash H, you get also 3 days, and that's it. Here. And how much you have altogether, it becomes 33,750. It's 9,000 plus. Right? How much it become? Somewhere here. It becomes 36, right? How much? 36?
Yes.
36,700. And what if you crash them all? Do you get any more time, any additional time? No. That's a waste. It will go just up. So this is actually your crashing process. There is no point in crashing this project anymore because it's a waste. Because you crash only the critical. So you see, from this assignment you can examine 2 things, or you can try to remember 2 things. First you have to find your critical path, and then you have to order, or you put them in order. Which one is the one that I should crash at first? Let's say here, if I tell you, well, when you crash, I don't want you to overrun the budget with more than 28,000 crores. Your original estimate is $22,000, for instance, and your maximum budget, your max budget, is only 28,000. Which one you are going to crash? Obviously, you will crash A, and then you will crash B, and you will not crash H.
In the E case, there could be 28,200 instead of 27,750.
How much?
28,200.
Yeah,
Let somebody check.
yeah, I agree, I trust you. Then this will be 7,
Yeah, correct.
right, 9, 7.
3,400.
You can, if you want. You can. This is the 37,500 total. Anyway, the numbers, we can check the numbers, no doubt. But this is, just remember this approach. So this is actually the diagram that shows it all normal, crash all. As you can see, beyond crashing A plus E plus H, nothing really. There is no point in doing it. Any questions to crashing?
How often should you check for a new critical path?
After each crash, you
After
should
each
check.
element crash, or after each, like you've done here?
I would check it after I exhaust the possibilities that lies within this critical path. Then I will go and look for the rest of the system. Like here, I have drawn the network now, right, in a full, without crashing. After I crash, I will go and draw it again, as you can see here. This is the network after crashing, after I have utilized all the possibility in that network. And now look there, and then we can repeat the same process and see what happened. Is there any new critical path that has arrived? We can do that now, actually, to see the difference. Because it's an interesting question when you have to check. Well, check after you complete your critical path.
Yeah, but you also said that you should always crash the cheapest part. But wouldn't it sometimes be cheaper to crash the most expensive in case that leads to another critical part step?
Yeah, if you are willing to sit and experiment
Yeah,
with
my
that,
question is like, how do they do it in bigger projects?
It's computational programs.
Okay.
It's not never by hands. It's a computational problem. It's an optimization problem. It's calculations. We have no chance to show them. But let's look at the network after crash. So you have A. Now A is no longer 5, it's only 3. And B is, we didn't crash P, right? So I will not put anything. I only crashed A and D and E and H, right? So I didn't crash B. I will leave B as it. And I have C. Did I crash C? No. And what is the duration of C? It was 3. And let's put here D. Did we crash D? No. D was not able. We were not able to crash D. And let's look at E. Did we crash E? Yes. How many days we crashed E? Remember? 3, right? It becomes 6. And F, did we crash F? No. F is still the same. And did we crash G? F4. Yes, thank you. And what about G? 6. And then finally H. And which is, we have crashed H, which is 5. Correct? Making mistakes. A is crashed, E is crashed, and H is crashed. G and F and B and D were not crashed. Okay, let's do the same process again and check if anything happens to our critical. Because anything happens to critical path, then we have to revisit the problem again. And then this one, right? Okay. So 0, 3, 3, 10, 3, 6, 3, 8, correct? Become 8, and then become 10, right? 8 plus 6 is 14, 10 plus 14, and here, what else we can do? 8, 14, it becomes 14, 14 plus 5 is 19, 14, 14, 8, 14, 10, 14, 8, 8, 3. You get the point now. Now, here we have 8. And here is 10. And here is 3. And this is 5. And 3, 5, 3. Gives you 3 is 0. So, this is a new situation after you have crashed. After you have crashed, you crash. This is still critical. C is not critical. E has become critical. B has become critical. F has become critical. H has become critical. And G has become critical. Now, if you want to crash even more, what you will be crashing? Now, here you have no more to crash, correct? Nothing to crash. And here you can't crash anymore. And here you can't really crash anymore. And H you cannot crash anymore. What you can crash again, what is left for you to crash is the G and the F. Yeah. And B, do we have B? Yes. B. So now, if you want to crash, your priority will be, it's either B or G or F. But which one of them you will crash? Now, why not?
Because it will not give any advantage in time.
Why not?
Because the
But you still B, for instance, has, you can crash it with 1 day.
yes, but then the critical part will be H, D, E, H, and it will still be 19.
Can we test it?
Right?
Yeah, let's test it. I haven't tested actually before I come, but I would like to do that. Huh? Yeah, possible, but let's take it on the platform. Test this hypothesis. I'm not sure, I don't know. Let's do that. I like that you had a quick brain, but let's do that. Now, this network is dead. We finish with this network. We are in front of another network, and the other network, what it says to us?
Writing on something.
It says to us now, in this situation, you have total duration is 19, correct? And you can't do anything with this, and you can't do anything with this, and you can't. You have utilized everything here, and you have utilized everything. The only thing you can crash is B, F, and G. What if we crash now? What happens now? Crash B with 1 day. What will happen? What will be the new duration of B? 6. So let's test what happens now. So your network now is 3. And here is 6. This is B. This is A. And this one is F. What if we crash F? What will happen if we crash F? It is from 6 to 3. It's 1 day. So F becomes 5. Correct?
3.
How much? 3, yes. Sorry. And here's your H. And the H is 5. Look at this one. Anything happens to this path? 3, 6 plus 9, correct? And here is 9 plus 3 is 12. So these 2 days are gone. Correct? Right? And what if this C is as is not critical? It is, we didn't change it whatsoever. So the C is still at 3. And we have this connection. It is 3. 3 plus 3 is 6. And there's the D. D is fixed, 5. Didn't change. So we have 3 plus 5 is 8. And then you have your E. E is 6. This is fixed. We cannot change. We are not able to change anything. Then you get, what should be here? 8. And for right. And let's say this is the G. Can you crash it? If you crash the G, how much you can crash it? The G you can from 6 to 4. 2 days, right? Do I see it right? Here is the G. 4. And it looks like this. And then 8, 12, 12, 14, and the H, you can do anything about it. So probably what we have here is 14 plus 5 is 19. So after you crash the critical path here, and even if you crash, this is what the problem says. You see other critical paths appeared, crashing them didn't make any difference in the as this is probably what you wanted to say. But at least we have verified. Crashing other critical activities in that situation didn't contribute to anything.
Is that always the case?
No, I wouldn't say that. Or I must say I cannot generalize. It could happen that when you crash your critical path, it appears another critical path that become dominant. Here, although other critical paths appeared, but the most dominant one was this one, all the time. So I don't know. I can't really say if this is a special case or not. But generally, check the critical path after you crash. If there is need for more crashing, look at the critical path that might have appeared. See what can you crash there. Okay? In the next lecture, now we will go to the third subject, which is resource planning. What we do with resources all the time, we play the game here, providing that people are available all the time for us to do these jobs. But in reality, they are not. So we have to do something about this. 15 minutes break. Duration of one given activity X, we get it directly in days or in weeks or in months, and it was very direct. So the duration was defined first, and then we continue with the network analysis. Now, in engineering projects in general, that results in producing something, developing something, we usually identify the scope not directly with time, but we identify the scope using man hours, or if you want, person hours. And from that description, we studying the availability of the resources we have, and perhaps the productivity of these resources we have, we define or we calculate the number of days or the number of weeks this project or this web package needs to be completed. Example. Again, now you have one web package X, and rather than saying that it should be completed in 3 days, let us say that it has a total workload of 120 hours. From previous work, from previous experience, if we put one person in doing this job, this person is able or will be able to complete it in 120 hours. Okay? So this is the very first piece of information we get. And then the second piece of information we get, which says that how many people we have available for this particular web package. And let's say we have 2. So we have 2 persons available in order to produce this 120 man hours. Is that enough? No. Another piece of information that we always have to consider is the productivity of these people. You know very well, guys, that people can get sick, right? Can take free. They go to take courses. They go and have meetings. Maybe they are busy with other projects, which means that when they start working on your task, they are not 100% available for you. They are not that productive. Or if you want, the number of effective hours per day or per week is not the optimal one. For example, in Norway, the optimal number of working hours per employee is about 40 hours. This is the register. This is what we get paid for. We come here and work every day from 8 to 4, and then we have this lunch break every day, I don't know, 20 minutes, I think. And you do that, if you work your week, you get 40 hours per week. But do you know how much actually people are working per week? The actual effective, the number of effective hours per week in Norway, like the time when they are really at work, are not sick or not on vacation or not traveling or not having fun somewhere else. You know how much in Norway? How much? Not 5, not that. It's not that. It's around between 25, 26, around this number. 25, 26. Per year in Norway, we say that in Norway, each employee should be working around 1,800 hours. But the actual workload is around 1,500. So you can 1,500 hours per year. That's the actual. And this is not the lowest in Europe. You know which country has the lowest? Not Italy, no. Guess which country has the lowest, absolutely the lowest in Europe? No, not Greece.
Spain.
No, it's the Netherlands. The Dutch. But you know, they are excused. It's allowed. And next verse, you know? Which next verse? I mean, the worst is the Dutch. And then there's a country here, and there's Norway. And which country is that? It's the French. It's France. Yeah. These two change position all the time. So France and Netherlands is the bottom in Europe. And you know which country is the highest? In the world. In the entire world.
China.
Not China.
Japan?
South Korea. 2,330 hours. Nobody can beat that. Anyone from South Korea? So that once the Germans are around 1,700. So it's quite in Europe. This is quite high number actually. But in Europe, the highest number is Romania, 1,950. That's Romania. This is the highest number in Romania. So my point here, you don't need to have to start competing now between each other, right? But my point here is that the available number of hours or the official number of hours is not the same as the effective number of hours. And that's why we have to correct.
But did you list the number of hours or the effective number?
No, what I listed is the effective. I told you in Norway it's 1,800, but the effective number is something around this number.
So Romania is the most effective?
Yeah, the most effective. 1,950. And in the world it's South Korea, 2,300 plus something. So what I wanted to say is that yes, it's true that you might have two people are available for you to do the job, but you should always look at what is the number of effective hours. The number they are really there are doing their job in order to be able to calculate the duration. And another factor that you should always think of in order to be able to calculate the duration is how do they work? What I mean by that? Sometimes, in many situations, you have two people here, right, from day 0, and then when they start working, they start directly, like full energy, right? They don't need time to get used to the job, right? So from day 0, they work fully, and they work so much hard until they finish the job and finish it. When people work with this style, we call it even or uniform distribution of effort. The first day, the way I work the first day is exactly the same as the second day, is exactly the same third day, and so forth. So I have some sort of even or uniform effort. So these 120 hours is uniformly distributed along the time. So the thing that I am missing actually is how much time I need in order to complete these 120 hours, providing that I have two people, and let's say they are South Koreans, and they are working 50 hours per week. And they work uniformly. So how many days or how many weeks I need? The equation is very simple. It says that, this is a a square or a rectangular, and this is missing, and the height is known. What is the height here? It is the number of people multiplied by effective hours, 50. So the height here is 100. So what will be the duration here? It is this 120 divided by
100.
how much?
100.
100, which is 1.2 weeks. Which is, if you want to convert them into days, how much they become? 8 days. Providing that you have 5 days. So this is now the difference. Before, previously, you got the duration, and this is how we are going to run it. But in some situation, what you get is the number of hours available, number of hours needed to be performed, and then you are told what are the resources available. You don't have more than that. And then you are told what are the effective number of hours, and based on that, you define your duration.
But do we assume here that the job is easily divided by 2?
No, this is the assumption that this is how they work.
Like I mean, if they don't know, dig in a hole, then there can be only one man digging at once. So we assume here that it is easily divided by 2.
Yeah, we assume here that we try to make the model as simple as possible, saying that these two will work as much. Or if you want, one of them will work too much and then another one will work a little bit, but we don't know who is doing what. We can't go into these details. Remember, guys, these are just models that are not able to capture everything in your project. Just models so that you can calculate something. But you see, here is a uniform distribution. But sometimes, in other situations, people don't really, when they start working, they really, from the first hour they go up to 100 hours, right? They don't do that. It's hardly done this way. So, how people do it? Sometimes we approximate it by this model. We say that people accelerate. All the work is getting accelerating. We start a little, and bit more effort, and then we flat, and then we decrease. This period is what we call the mobilization period. Here we mobilize resources. We don't really start with 2 people immediately, fully working. Maybe 2 people are there, but they are not fully working. One of them is lazy, the other one is working a little bit more. So, but a little bit, and then we come to the full effort, full gas. Right? And then, right before we finish, we start to de-accelerate or demobilize our resources. And usually, this period of mobilization period is given and demobilization period is given, and the problem becomes finding the normal period. Again, as you can see, it is simple mathematical problem. The area here, always what represents this area? What is this area under this curve? It is your scope for. Let's say it's 250. And your mobilization period is 1 week. Make it more, make it 500. And your demobilization period is 1 week. And again, you have 2 people. And they box, and they are also from, now this time let's say they are French. So, they don't work that hard. They only work 25 hours per week. So what will be the height of your, and if you have two people and they only work 25 hours, so what will be the height here?
50.
Well, maximum height. 50. Now this is a simple calculation problem. So what will be the duration now of this period? Can you calculate that for me? How can we calculate it?
500 divided 50.
Now first, you can look at here. How much is this? We want to find what is this part here. How much is this? What is the area here? It is half, right? Multiplied by 1, multiplied by 50, which gives you 25. So it says that in this period, this mobilization period, the total amount of work we will be doing with these two people is only 25. So here you have 25. And here it's a demobilization period, same is 25. So how much you left here with? 450. Can you find the duration now? It's very simple. T is 450 divided by height, which is 50, which gives you 9. So the total project duration is 1 plus 9 plus 1, which is 11. So depending on your profile, how people are going to work influence the work. It depends on the productivity of these people, how they work, how effective they work. It depends on the number of resources you have. That all these variables influence your duration. Now, what we do now, let's say we are facing a similar problem. We have a time constraints that we should adhere to, and we have resource constraints and that we should adhere to, and we need to balance these two. How to balance resources with time. This is the issue that I want to present to you. And again, it's actually a graphical issue. And it's a computational problem, this optimization of resources. We call it sometimes resource leveling or resource allocation. When we do resource leveling, we are only concerned about using this almost same amount of resources through the entire project. But when we are doing resource allocation, we are concerned with finishing with the shortest possible time. Okay. Example will illustrate my points. Let's take again a simple activity in Node, and we do it this way, and just one. And let's say that A has a duration of 5, B has a duration of 6, C has a duration of 5, D has a duration of 3, and E has a duration of 6. And all of them has a simple finish to start relationship. And let's calculate, as usual, the total project duration so that we know what we are talking about. Will be 11, 17, and 17, 11 here, 11 here, 8, 11, and here you get 6 and 11 here and 5 here and 5 here and 0. So our critical path is very clear. It is the A, B, and okay. Now, what if I tell you now additional information that I have for A, I need 2 people. I need these 2 people each week or each day of the week. Did we say days or weeks here? Just days. Then each day I need 2 people available for me. And here for B I need, let's say, 1 person. And for C I need, let's say, 2 persons. And for D I need 1 person. And for E I need 2 persons. Now I give you here the number of people needed directly. Sometimes, of course, you can get them in man hours and you have to make the changes. Now, can we draw, the question here, can we draw a diagram that shows how these resources will be needed along the timeline and say maybe we have a problem, we have some constraints? Yes, we can do that by looking into this diagram. And we have one time like this, and this is your time, and this is the number of people that you need. What is the total duration? Is 70. So maybe it's 5 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. This is the total duration. And let's look at A. A, it goes from 0 to 5, which means here. And how many persons I need? 1, 2, 3, 4, 5. How many people I need? I need 2. So this is our scope, depending on how much each one of them is worth. So this is A. And then, let's draw the longest. This one. It goes from 5 to 11. And how many people we need there? 1 person. 5 to 11. And I need only 1. This is my B. And then I have something goes from 5 to 10, which is C. C goes from 5 to 10. C. And then what else I have? I have something else goes from 5 to 8, which is the D. 5 to 8. 2 people for C? Yes, even better. I like that. Yes. I was thinking about that. This is C. Thank you. Ta-da. Correct. And then we have a D. 1 person. But we need this person only D. It's 1 person, right? Yeah. And then you have E, which is 2 people, which is how many does? 7. 2 people. So this is my Now, you see, this diagram that I have just drawn right now, this one, which looks like this, is what we call resource loading chart. You can draw it or you can make it in a table. If you put it in a table, it becomes resource loading table. So I always prefer to see it in a diagram. It's more obvious what are your possibilities. And notice also that we always use the early start and early finish when we make this diagram. Always early start and early finish. But keeping in mind the float. Now, why we do that? Now, let's say we have Houston, we have a problem. What's the problem, Houston? We only have 3 people. In our company, in the entire company we have, right now, in this period, from 0 until 17, because you are busy with other projects and so on, we only can give you 3 people. Can you solve this problem? Can we solve this problem? Can we make it in a such way that I adhere to this resource constraint? What can we do in this situation? I have only 3 people. Don't have more. And as you can see here, I need 1 person for 3 weeks from 5 to 8 in order to fill in the gap. What are the options I have in front of me? You think? What can I do? Yes.
And was equal than 1 person do task D?
I'm not sure what do you say. Task B is here, and I need 1 person to do this task.
Can it be crashed by using 3 people, seeing as C has a float of 1?
Yes. How do you crash it? Crash the D.
If you move C back a week, or if you place D at the end after C, you can use.
Yes. Now you start talking. You see what we see here. What we see here is a gap, right? And this gap is from 10 to 11. And where is 10 to 11? Here. So if you can, now if you don't want to change, I should emphasize, if you don't want to change the total project duration, then your only option here is to take advantage of this both thing that we talked about. Then what you need to do, rather than starting it at 8, because even if you start it at 8, you still have a problem here. So what you need to do is maybe to start it at 10, but then you have to crash it. Add more resources so that you can finish it in just 1 week. Because here you have available resources. You know, here you have at least 2 people, right? In this period, 2 people are available to you. And if you can do that, if you can crash D, move it, put it here, you haven't actually changed anything here, because it's still within the available time, with the available flow. But then you have to crash it, so that it can be done in 1 week. With this solution, you solve your problem. You have leveled your resources. You took advantage of all available resources, and you eliminated this resource constraint. If you can't crash it, on the other hand, what can you do? What else can you do?
All that time?
You have to Extend
Extend it.
project duration. Maybe how long we need to extend project duration to fix this problem?
2 days.
Look here. I have one week opening here. So if I want to solve this problem, and this is D and use 3 weeks, and I cannot crash it. So how many times, how long I should extend the project duration?
2 weeks.
2 weeks. I don't need 3. I only need 2 because I have a flow. That's why it's cool to see your flow. That's why we calculate the flow. So that we come here and look, aha, I have an opening here. Aha, I can stretch, or I can move, or I can break, or I can crash some part and leave other parts using the available flow. This is what is the idea behind the resource plan. Looking at the resources individually. This is also become important when we are going to draw the S-curve. That's a very important tool in project management. Drawing the S-curve. S-curve, it's a curve that shows the accumulated land costs. These people are working. They are going 100 hours here, 50 hours here, 60 hours here, 20 hours here, and 30 hours here. So if we want to draw a diagram that shows the accumulated land cost at so that we can go and check at any time. This is the job of the S-curve. And the S-curve is our ultimate tool if we want to conduct follow-up on our project. I'll show you. This is you have to learn how to draw your S-curve. In the next lecture, we will almost only talk about the S-curve. And we draw the S-curve with this in mind. This is our reference. We have to have this kind of diagram to draw the S-curve. So let's take an example. Many examples today. Okay. We have just one activity, and we say A, and this takes, let's say, again, 5. And this is a B, duration of 10, and this is a C, duration of 50. And this is a D, duration of 5. And in addition to this information, let me tell you that there are 2 people will be working. And each one of them works 30 hours per week. And just to say, these are weeks, okay? That's our calculation in weeks. So each 2 people, each one 30 hours. And then one person works 30. And here 2 persons, each one works 30. And 1 person, each one works 30. So what will be the total scope of A per week? How much? 60. And for B, 30. And for C, 60. And for D, 60. Okay, now let's go to our diagram and let's draw 0, 5, 5. We want to draw the S-curve, by the way, now. This is our tool to control the performance of our project, something we will see next lecture. But this is like just a taste of it. 20, 25, 25, 20, 20, And here become 10, 9, yeah, 5, 20, 10, 5, 0. So, now, if we want to draw the S curve, we know that the total project duration now is how much? 25. So let's say 5, 10, 15, 20, 25. And how much resources we need to complete A? It is 5 weeks. And in each week we produce 60. So what will be the total scope for A? 300, right? Are you agree with me? 300. And what will be the total scope for B? 10 multiplied by 30, 300. And what will be the scope for C? 60 multiplied by 15, how much? 90? 900. Very good. And for D, 30 multiplied by 500. So what will be our total scope? Like when we finish this entire project? 300 plus 300 plus 900, how much it become? 600, 1500 plus 150. Yeah? 16. So the total scope for this project is 1650. So after 25 weeks, and now here I can make nice, we say 100, 2, 3, 4, 5, 6, 7, 8, 9, 1000, 200, 300, 400, 500, 600, 600. Here. This is our accumulated cost. Accumulated cost after 25 weeks is 1,650 hours. But how they will look like? This is the S curve. How we go from 0 to 1,650. Now, be patient with me. A, after 5 weeks, the accumulated costs or the accumulated man hours is 300. Then, and what is the duration of A is 5. After 5, I accumulate so much, 300. And after 15 weeks, how much I accumulated? How much I have accumulated after I finish B? 300 from here, correct? But how much from C?
9.
How much from C?
600.
No, 1,000.
600, right? For the because we have 60 and 60 multiplied by 10 becomes 600. 600 plus this 300 become 900. So after 10 weeks, which means here, I have 900 plus this 300 from before. So how much I get? 1,200. So this is the accumulated costs after 15 weeks. What about after 20 weeks? How much it become? The end, because C is not finished yet. I still have 5 weeks. And 5 weeks multiplied by 6 become 300. 300 added to this 100, 1,000, 1,200, you get this. And this is your final point. And then you interpolate them. That's your, of course, when the things become bigger, it will really look like an S, by the way. This is your S curve. And this is the thing we are always looking for when we are planning or we want to control anything. Because I can come and tell you, guys, at the end of this week, what was the plan? What was my plan? You tell me, your plan was 1,000, 1,200 hours. And I tell you, but how much I really have used? You know, this is my plan, but I ask you how much really these people send time hour. You tell me, oh, these people, they were mad. They send you 2,000 hours. In our calculation says 2,000 hours. They billed us for 2,000 hours. And then I tell you, okay, fine. They billed us for 2,000 hours. But how much they really have produced? What is the value of what they have produced? And you tell me the value of what they have produced is 500. Now can you tell me what kind of project is that? And how it will evolve? And how it will develop? The plan was 1,200. You produced 2,000. Oh, now you billed me 2,000. But you produced 500. So what is the situation of this project? What happens if we continue to do like that? This will be the subject of your next lecture. See.